All right, today we're going to talk about something that sounds like it was ripped straight out of a sci-fi novel, but it's very, very real. We're talking about computing with living human brain cells. Welcome to the Wetware revolution.
Okay, let's just start with a number. 1,400 watts. That is the insane amount of power that a single next-generation AI chip can pull. To give you some perspective, that's more than a lot of household microwaves. And that number, well, it points to a gigantic problem.
You see, the explosive growth of AI is starting to become physically unsustainable. All that power needed to run these advanced models generates a ton of heat. So that means you need equally huge energy-guzzling cooling systems just to keep them from melting. The cost, the energy use, it's all skyrocketing. It really forces us to ask, is there a better way to do this?
This energy crisis means we are slamming right into what you might call a silicon wall. Our demand for computing power is growing exponentially, but our chips just can't keep up efficiently. So scientists are being forced to look for a solution that isn't just a small step forward, but a completely radical leap.
And that radical leap? It might just be synthetic biological intelligence, or SBI. The pioneers in this field, a company called Cortical Labs, asked a really brilliant question. Instead of spending billions trying to simulate a brain on silicon, why don't we just use the real thing? And SBI does exactly that. It uses actual living neurons as the computer's processor. So how on earth does that actually work? I mean, it sounds impossible, right? Let's break down the mechanics of how you actually compute with living tissue.
The whole thing works as a four-step loop. First, you take digital information, let's say from a video game, and you encode it into simple electrical pulses. Step 2, you use those pulses to stimulate the living neurons, which are sitting right there on a special microchip. Third, and this is the magic part, the neurons process that info by physically changing. They actually rewire themselves, forming new connections. And finally, the chip decodes their electrical response back into a digital output. It's a real, direct conversation between silicon and cell.
Now, this table really gets to the core of what makes these systems so different in how they learn. You see, traditional AI uses a pretty slow, brute force mathematical process to get better. But biological computing, it runs on something called the free energy principle. Now, just think of it like this. Living things hate being surprised. A fish does not want to be surprised by a shark, right? Well, in the same way, our neurons don't like getting hit with unpredictable, chaotic signals. So when the system makes a mistake and gets zapped with a burst of chaotic static, its version of a punishment, it literally rewires its own connections to avoid that surprise next time. It isn't just adjusting some numbers in an algorithm, it's physically changing itself to learn.
So that's the theory. But the all-important question is, does it actually work? Can you really teach a bunch of cells in a petri dish to do something useful? Well, the answer is a pretty resounding yes.
The first huge proof of concept landed in 2022. It was an experiment they nicknamed Dish Brain. Researchers took about 800,000 neurons, put them on a chip, and successfully taught them to play the classic video game Pong, acting as the paddle.
And here's the part that is just absolutely incredible. It didn't take weeks of training or even days. The cells started changing their activity and learned how to successfully hit the digital ball in just 5 minutes. That's a level of learning efficiency that is just staggering.
Okay, so playing a simple 2D game like Pong is one thing. That's amazing. But could a system like this handle a challenge that was way more chaotic, way more unpredictable, and just exponentially more complex?
And just recently, they did it. They trained a neural culture to play the legendary 1993 first-person shooter Doom. Now think about that. This requires navigating a 3D space, identifying enemies, making split-second decisions, and the results were incredible. The system's success rate shot up from a baseline of just 4.5% to 46%. It was genuinely learning to play Doom.
Now, as amazing as all this is, and it is amazing, the real revolution here isn't actually about playing video games. It's about energy.
And this right here, this is the number that really matters. Just take a look at this chart. That tiny little bar way over on the left, that's the CL1 biological computer, including its whole life support system, running on just 30 watts. Now compare that to the silicon AI chips, which need 700, 1,000, even 1,400 watts. The difference isn't just big, it is a total, absolute game changer. This is the economic advantage that could change everything.
And to put that in perspective one more time, your own brain, one of the most powerful computers in the known universe, runs on about 20 watts. The CL1 runs on just 30.
This kind of efficiency basically gets rid of the need for those giant, expensive, power-sucking cooling systems you see in data centers.
An efficiency leap this huge doesn't just make AI cheaper, it opens up a future of applications that, until right now, have been pure science fiction. So let's take a look at what this new wetware could actually build.
For starters, this could solve something called more of X paradox. It's this weird fact that for traditional AI, super complex math is easy, but simple physical things, like walking on uneven ground, are incredibly hard. Biological computers, because they evolved to interact with the messy real world, are amazing at this stuff. This could be the key to building robots that are actually fluid and adaptive.
And the applications just keep going. I mean, imagine personalized medicine, where new drugs are tested on a tiny clone of your own neurons before you ever take them. Or what about recreating diseases like Alzheimer's in a dish so we can finally understand them? It even opens the door to human augmentation, the idea of matrix-style learning, where skills could be uploaded right into your brain.
But as we start to blur the lines between living tissue and machine, we run headfirst into some of the most profound and difficult ethical questions of our time.
This quote really gets to the heart of the dilemma. Remember how these cells learn? By avoiding that chaotic, punishing signal. So bioethicists are starting to ask, if the system's entire learning process is based on avoiding something that is the biological precursor to pain or stress, are we essentially creating digital suffering? Are we building an entire industry on engineering microscopic distress?
And that brings us to the final, haunting question. This technology absolutely shatters the line between a living thing and an inert machine. It promises a future with unbelievable power and efficiency. But it forces us to ask, if a computer can only learn by avoiding a state that looks an awful lot like suffering, what in the world have we created? And what does it mean to scale that idea across the entire globe?